Hello and welcome back to PC Retro Programmer. In this video I'm going to go through a fairly straightforward implementation of Bresenham's line drawing algorithm in assembly language for CGA mode 4, the 320 by 200 4-color graphics mode. Now if you have a look at the algorithm here, it's pretty straightforward. There's just a single loop and a single conditional, an if statement here. And the algorithm just takes the endpoints of the line as inputs, and then it will draw all of the points in the line between those endpoints, including the endpoints. So there's a pair of coordinates for each endpoint, and the first thing that I need to discuss is the different versions of Bresenham's algorithm that we're going to need. So because we're working in CGA, the process of moving to the right or to the left is very different than moving up and down on the screen because of the way CGA memory is laid out. So we need one version of this algorithm for horizontalish lines, lines that are more horizontal than vertical, and another version of the algorithm for verticalish lines, for lines that are more vertical than horizontal. So this particular version here is for horizontalish lines, and we'll talk about one for verticalish lines in another video. So horizontalish, just the width of the line has got to be greater than or equal to the height. And so in other words, the difference of the x coordinates has to be greater than or equal to the difference of the y coordinates. So in these variables here, it'll be dx greater than or equal to dy. Now we're going to make two other restrictions as well. These would normally be artificial, but I'm going to make them here again because of CGA. So in order to make things simple, I want x1 to be greater than or equal to x0 and y1 to be greater than or equal to y0. In other words, both of these values will be non-negative. Now you can always guarantee one of these. For example, if dx was negative, what you could do is switch the endpoints around. So just draw the line backwards, in other words, from end to the start. And that would switch the sign of dx, and you'd end up with a positive value instead of a negative value. And if it was 0, it would just stay as 0. So you can always demand that dx is greater than or equal to 0, but you can't simultaneously demand that for dy. So in the end, we're actually going to end up with 4 different versions of this algorithm because of the need to deal with negative dy's. But more about that in a later video. For now, dx and dy are both non-negative. Now, in order to make this a really efficient implementation, we're going to try and keep as much in registers as possible. So let me just bring up the implementation that I've done of this, and then you can have a look at how I've actually allocated those registers for maximum efficiency. So just in the DOS editor here, we've got CGA line, and these are the 4 inputs that we talked about. There's a 5th input, of course, the color of the line, the color of the pixels we're going to draw, which will be one of the CGA colors, 0, 1, 2, or 3. And that color can fit in 2 bits, but we'll just use a byte here, that's certainly plenty. And these are the conditions that I talked about, horizontalish, dx is greater than or equal to dy, and the other 2 conditions, which will make things easier to understand, and also we'll need this for CGA. So now let's take a look at how to allocate registers here. Obviously in the main loop, we have d, dx, and dy that are used pretty commonly. And we should put those in registers. Now, this particular version that I'm going to show you, I'm not actually going to use a plot function, and I'll explain why in a moment. But that means that we won't need to keep x and y at all, let alone in registers. So that's good. So far we only have 3 different values that we have to put in registers. Now if you look at the for loop here, it looks like we need x0 and x1, but it turns out that because we're not going to use x and y, we don't really need these. We can actually just deal with the number of iterations of this loop. So that'll just fit in a single register instead of 2. So that's the other saving that we're going to make here. So the number of iterations is actually equal to the number of pixels in the horizontal direction because it's a horizontalish line. That's the characteristic of a horizontalish line, that you always move 1 pixel to the right every iteration. You may or may not move 1 pixel down, but you always move 1 pixel to the right every iteration. So the number of pixels is just a number in the horizontal direction, which is just x1 minus x0 plus 1. The plus 1 is just because we're going to draw both endpoints. And so that's all we need to keep here. We just need to keep the number of iterations. So I'll need a register for that. So let's go through those and see what we actually need. So dx, we need 319 minus 0 would be the worst case. If we were going all the way from the left of the screen to all the way on the right, the x coordinates could be 0 and 319. So that won't fit in 8 bits. We need a 16-bit register for that. In the y direction, we could go from the top to the bottom of the screen, or 199 minus 0 here, and that would fit in 8 bits. But then if we look in the algorithm itself, we see that we don't actually use dx and dy on their own anywhere. It's always 2dx and 2dy, and those values won't fit in 8 bits. We'll need 16-bit values for both of those. So dx and dy will be 16 bits, and of course d has to be at least as big as dx, so that's as well got to be 16 bits. And again, the number of iterations has got to be 16 bits, because it's really just counting the pixels in the x direction. Alright, so let's have a look at how I allocated these over in the implementation. So I used the dx register for 2dx, I used bp for 2dy, and si for d. So those are all 16-bit registers. I did use BP here. That's a general purpose register, so it's completely valid to use this. But remember that BP is used to access the arguments of the function. So I really need to make sure that I'm done with all the arguments to the function before I put anything in BP. But that'll turn out to not be a problem in our algorithm here. As I said, x0, y0, x1, y0 are not used in the main loop. And as I said, we're not going to use them here either. We're just going to replace this with a count of iterations. Now, I said we're not going to use a plot function, and the reason for that is because in CGA this is really expensive. It's about the worst way that you can draw graphics primitives. You don't want a separate function for drawing pixels. Such a function would have to compute the offset in CGA memory, which at least has to do a multiplication by 80 at some point, and that's expensive. And then it has to compute which bits have got to be used inside the byte at that location, and then it's got to do shifting and so on to update the pixel. So it's very, very expensive. So instead, we're going to keep the offset in video memory updated at all times in this algorithm. So when we want to plot a pixel, we already know exactly where we're going to put it in video memory. And we're also going to keep all the necessary information for plotting a pixel at that location. So a mask and a color up to date and shifted into the right bits all the way through the algorithm, so through every iteration. And so whenever we move to the right or to the left or up or down, we're going to update all of these values accordingly. So that'll mean that we don't need registers for x and y, but we will need registers for the offset in video memory. So I've allocated di over here for that, and for this mask and color information. So we use di because then we can use the assembly language instruction stosb to write a byte into video memory. Remember, stosb writes the value in AL, the byte in AL, to memory at the location esdi. So ES is the segment and DI is the offset. So we'll make ES the CGA segment, and then we just need the offset in DI. So that makes complete sense. And obviously to draw a pixel, the process is to take the byte out of video memory, put it in AL, mask off the bits that you want. So this is just a logical AND operation with a mask, which we'll store in BL here. And that'll just have zeros at the 2 bits that we're interested in, and ones everywhere else. So in other words, it just zeroes out the 2 bits we're interested in. And then we fill in those bits with the color we want. We have the color obviously shifted into the right place. stored in BH. So we'll just need to do a logical OR with BH into AL. And then finally you write AL back into video memory using this STOSB instruction. So those are the 4 standard steps for drawing a pixel, and so we'll just keep the mask and the color bits shifted up to date with every iteration of this algorithm. So that's one 16-bit and 2 8-bit registers. And as I said, we'll also need the number of iterations, which will go in CX. And the reason that we use CX is because then we can use the assembly language loop instruction, which works with CX for a loop of a certain number of iterations. So everything works out beautifully here. The only other register we have left is AX, but of course we need that for just doing general computations. We use it as an accumulator. So for example, when we copy a byte out of video memory, it's got to go somewhere, it'll go in AL. So let me now go through the implementation itself and explain how it works. The program starts in the usual way by saving the usual registers in case we want to call this function from C program. Now I'm not going to be touching DS or SP, so I don't need to save those, but I do need to save BP, SI and DI. And of course I set BP up in the normal way to be able to access the arguments to the function, which are on the stack. So we just copy the stack pointer into BP. And the first thing that we want to do is set up the CGA segment. Now we know that that's at address B800, that's its segment address in memory. And we're going to put that in the ES register because we're going to be using the assembly STOSB instruction, which writes at ESDI. So ES has to be the segment address and DI will be the offset address. And remember, you can't put a value directly into a segment register, you have to go via a general purpose register. So we just use AX for that. So now we compute DX, which is just the difference of X1 and X0. So I just load those into registers and do the subtraction. And notice that I put X0 into DI and I don't modify it, so I'll be able to use that below when I need X0. So the first thing that we want to do is compute the part of the offset that is corresponding to the X coordinate. And remember that that is given in CGA by X divided by 4, because there are 4 pixels in a byte. So the offset byte will be X divided by 4, and of course we're starting at X0, Y0, so the X coordinate that we're interested in here is the X0 value. And so what I do here is I make a copy of X0. Remember, it's in DI, we put it in there in the previous step. So I make a copy of it because I also want to compute X0 mod 4. That's the pixel within the byte that we need to modify. This is straightforward. In assembly language, to do a value mod 4, you just AND with 3. That just gives you the bottom 2 bits, which is exactly the same thing as taking the value mod 4. So it's just a little mathematical trick. And dividing by 4 is the same as shifting right by 1 bit twice. Each of these will divide by 2, so we get a total of division by 4. So now we have CL contains the pixel within the byte, and DI contains the offset, at least the X coordinate part of the offset. So now we want to compute the color and mask bytes, and these have to be shifted by the number of pixels that we've now got in CL. First of all, we load the color up into BH, and that'll be in the lowest 2 bits of BH, of course. Now, instead of putting the 0 bits of our mask in the bottom 2 bits of BL, I use a little trick here to save some rotation. I put the 0 bits in the top 2 bits, which is exactly the same as if I'd already rotated by 2 bits. So the reason I do this is because it saves me a rotation by 2 bits. Rotations are expensive, and so if I can save any, that's always good. So I'm actually going to need to rotate the color just a little bit further because the color doesn't come in the top 2 bits, it comes in the bottom 2 bits. So there's 2 extra bits of rotation that I need there. Now I've got the number of pixels that I need to rotate by in CL here. To get the number of bits I need to rotate by, there's 2 bits per pixel, I have to multiply CL by 2. And so that's what I'm doing here. The shift left multiplies by 2. So now I can actually rotate by that number of bits. So I first of all rotate my mask by that number of bits, and that gives me the correct position for those 0 bits in the mask. And now I rotate the color, but as I said, I need to rotate the color an additional 2 bits because they're not quite in the right place when they come into BH. So then that just means I have to add 2 to the number of bits I've got to shift by, and that's what these 2 lines are for. So now the color and mask are computed and they're in the right bits for that first pixel. And the next thing in the algorithm is to compute the number of iterations. And because it's a horizontalish line, the number of iterations is just the number of horizontal pixels. So it's just x1 minus x0, which we've already computed, that's dx. So I put that into cx, which will be where I keep my iterations for my loop. I'm going to use the assembly loop instruction. Now I'm also going to draw the final pixel on the line, the endpoint. Some algorithms call for lines that don't draw the endpoint, and other ones you want to draw, all of the points, including both endpoints. So this one I'm going to draw the final endpoint, and so it's actually x1 minus x0 plus 1 pixels. So I need to add 1 to the iterations here. Okay, so now I need to compute dy, actually 2 dy. So I just compute y1 minus y0, so I load those values into registers and do a subtraction. And to get 2 dy, just multiply by 2, which is a shift left by 1 bit. Now notice that I'm using the BP register for the first time here. So after this point I won't have access to the arguments to my function. But fortunately I've used all the values and everything I need is in registers now. I've laid this out carefully so that I don't need to access them again, so I can put something in BP. And it's fine to modify BP on this line because y1 will be read from the memory, from stack, before it's written into BP. So this is absolutely fine to do this, but after this point I can't access the arguments again. So now I need to compute the part of the offset corresponding to the y coordinate, and there's 2 parts to that. First of all, remember that CGA memory is set out with all the even lines first, then all the odd lines. And if it's an odd line, I need to add 8192 to the offset. So in other words, if y0 is odd, I've got to add 8192 to di. So how do I do this? Well, if you look up the shift right instruction, you'll find that it actually puts the bit that gets shifted out into the carry flag. So if y0 is odd, the carry flag will be a 1, otherwise it'll be a 0. So how do I use that information? How do I turn that carry into an 8192? Well, that's what the magic of the next 2 instructions are. This is a really neat assembly language trick. What you do is you subtract a register from itself, so that'll just give you 0, but you do a subtract with borrow. In other words, it subtracts the carry flag as well. So it's 0 minus the carry flag. So if y0 was odd, this will end up giving us a value of minus 1. And if y0 was even, this will give us a value of 0. Now minus 1 is just all 1 bits in its representation, and 0 is just all 0 bits. So now we just AND that with the value we're interested in, 8192. So if it was all 1 bits, ANDing with 8192 just gives you 8192, and if it was all 0 bits, you just get 0. So now we've turned the carry into a value, and then of course that 8192 needs to get added to the offset if it's there, otherwise it would just add 0 to the offset. Alright, so that's a really neat trick, and the final part of course is to take the y coordinate divided by 2 and multiply by 80. There are 80 bytes per line, and of course we're now only counting odd lines or even lines, depending on which case we're in. and so it's y0 divided by 2. So this is a trick for multiplying by 80. So first of all, we multiply by 16. Remember that y0 is in AX because we put it there earlier. Actually y0 on 2 is in AX because we computed y0 on 2 at this step here. All we need to do is multiply by 80. So we multiply by 16 first. That's just 4 shifts left, and add that to the offset. Then we multiply it by an additional factor of 4. So it's an additional 2 shifts. So now we've multiplied by a total of 64 and add that to the offset. So 16 times y0 on 2 and 64 times y0 on 2 is 80 times y0 on 2. It's not actually really the fastest way to do this. I'll show you that in a later video, but this is much faster than calling a mul instruction. Then there's just a couple of minor things left before the main loop. We just need to compute the initial d, which is minus dx. We've already computed dx, put it into SI and negate, and then we want 2 dx, and so we shift left by 1. So now everything is set up and we're ready to do the main loop of the program. Well, our loop starts with a label, which we jump back to using the loop instruction below. And remember that a label isn't an assembly language instruction, it's just a label in the code, so the assembler knows where to jump to. And the first thing that we have to do inside our loop is to plot xy. But as you recall, we're not keeping x and y coordinates around, and we're not calling a plot function. We've got everything already set up so that we can just get the byte from video memory. We can do our AND with our mask, we can OR with our color, and we can write back to video memory. So this is just a standard pixel writing routine where everything's already set up for us. We computed it in the prelude and it'll be kept up to date now at every iteration of this loop. So the next thing is to add 2 dy to the decision variable d. And so that's just a simple addition, of course. And then we want to do an if statement. Now normally you'd have a comparison here. You'd have the CMP instruction to compare SI with 0. And you want to compare D with 0 to see if it's greater than 0 or not. But you don't need to do that here because we've just modified SI, and all of the flags for telling whether something is greater than, equal to, or less than 0 are already set because it was the result of this arithmetic operation. So you don't need to call the compare instruction to compare with 0. You can skip that if you've just done an arithmetic instruction which will automatically set those flags. And when do we want to jump? Well, we want to jump if we want to go over the body of the if statement. And we want to go over the body and skip it if d is less than or equal to 0. We only want to execute the stuff in the body if it's greater than 0. So we want to jump if SI is less than or equal to 0 here. Now notice this is a signed comparison. We're comparing with 0 here. We want to know whether it's a positive or negative value. And so this is a signed comparison. So we use JLE, not JBE, which we'd use if it was an unsigned comparison. And of course we're going to just jump over it to a label that we'll put later called line skip y. So what's in the body of the loop? Well, the first thing is to increment y. And this is a little bit complicated in CGA, as you recall, because you have to deal with going from an odd line to an even line, and from an even line to an odd line. So what we do is we just start off assuming that we're going from an odd line to the next even line. So the way that would work is you'd first subtract 8192 to get back to the even bank, and then you'd add 80 to go to the next even line. And so that's a total of a subtraction of 8112. So 8192 minus 80 is 8112. But of course that might not have been what we were supposed to do. We might not be going from an odd line to an even line. We might have meant to be going from an even line to an odd line. So if we did the wrong thing, we'd need to add this value back on, and we'd need to add a further 8192, which is what you do to go from an even line to an odd line. So this may not have been the right thing to do, but if this was the wrong thing to do, there'll now be a carry, because we've actually subtracted a value from DI that would have made it negative. We can only subtract 8112 if the value was large enough. In other words, if we were in the odd bank in the first place. So if this wasn't the right thing to do, we're going to have a carry, and then we use our trick to turn a carry into a value using a subtract with borrow and an AND instruction to add 16304, which is basically adding this back on plus the 8192 that we need to get to where we should have been. And so that's what we're doing here. We just add that onto DI. So either 0 or 16304 is going to be added to DI here, depending on the carry status here. And the carry status here just depends on whether or not this was the right thing to do. So this is a very, very short sequence that allows us to increment the Y offset. Now the next thing inside the loop body is to subtract 2dx from d. It's just a simple subtraction. And there's the end of our if statement. That's the label for the end of our if statement. So the only thing that remains now is to increment the loop counter, which is basically the equivalent of incrementing x, and to do the loop. So incrementing x for us means to move 1 pixel to the right. So that's basically a rotation by 2 bits if it's in the same byte, and if it's not in the same byte, we still have to do the rotation by 2 bits, but we also have to add 1 to the offset. So here is the rotation by 2 bytes. We rotate our color and our mask by 2 bits. So how are we going to tell whether or not we need to also jump right by 1 byte? Well, we can just look at the mask. The bottom 2 bits of the mask would have been 0 if we were shifting zeros out the bottom. And the cool thing about this rotate instruction is that as well as putting those 2 bits into the top 2 bits of the mask here, it also sets the carry flag to the last one of those bits that we shifted. This line here will shift a 0 into the carry flag if we've already shifted all the way through the byte. And that's precisely when we need to move along to the next offset, because we've already done a full rotation around. So in other words, if the carry is 0, we need to increase the offset by 1. Well, that doesn't look like what we're doing here, so I must have messed up somewhere. But in fact, I haven't, and the reason is something I didn't mention earlier. The STOSB instruction up here doesn't just write the byte into video memory, it also increases the offset, the DI register, by 1. So we've actually already increased the DI register by 1 unconditionally. And so what we actually need to do is to correct that if it wasn't the right thing to do. And that's exactly what this sub with borrow will do. It'll subtract the carry from DI and go back if there was a 1 in the carry. And there's a 1 in the carry precisely when we aren't shifting zeros out the bottom of the byte. So in all the other cases. So this is precisely the right correction that we need in the case where we weren't supposed to shift right by 1 byte in the offset. So that's basically all there is to it. We just then loop around to the start of the loop until the iterations finally go down to 0. The iterations are in the CX register, of course, and then we're done with our main loop. So at this point the line is now displayed on the screen, and of course we can just pop our registers and return from this function. So that's basically all there is to that, and so now we need to have a look at a driver program to actually call this function. I'll run through the main program quite quickly because in some sense it's the least important part of this video on line drawing. So of course our main program has to have a starting point, and we'll tell the assembler about this starting point at the very end. So it just needs a label, and I'll just call it start. Now the first thing I want to do is go into CGA mode 4, the graphics mode, and this is done with bias interrupt 10H, the video interrupt, and the function number is 0, set video mode, and the mode is mode 4, the graphics mode. So now we call our line drawing function, and of course before we do the call we need to push all the arguments onto the stack. So remember they go in reverse order, so last argument goes first, and so that'll mean color has to be going on first. So I'm going to draw a line in color 2, so I put that in AL. Now I can't actually push just a byte. Remember the color argument is just a byte. I have to push a whole word, and so I have to push all of AX. It'll ignore the top part in the actual function, but this is still required. Then I'm going to draw the line from coordinates 0, 0 to 200, 100, and it has to be a horizontalish line, so the difference in x coordinates has to be bigger than or equal to the difference in y coordinates, which it is, and both of those differences have to be non-negative, which they are. So I'm going to put the values in AL, and of course I need AH to be zeroed out, because these are actually 16-bit values in our function. So I'll XOR AH with itself to set it to 0, and then I can just put the coordinates in AL. So 100 goes in and push AX, 200 goes in, push AX, 0 goes in, push AX twice because we have two 0 coordinates, and then call our line drawing. Now at this point the line is displayed on the screen, and when that comes back, it's our responsibility to clean the stack up. So we've done 1, 2, 3, 4, 5 pushes, 10 bytes, and so we need to move the stack pointer back up 10 bytes to clean up, and so that's our function call and clean up complete, and we're back to the way things should be. And of course I don't want the line to just immediately disappear off the screen as soon as it's been drawn. That will be not visible if I do that. So I'm going to wait for a key press just so that we've got time to actually look at it. And that's bias interrupt 16H, function number 0, wait for key press. And I think you can press pretty much any key on the keyboard and it'll register a key press. So finally, we want to restore the original video mode before we exit to DOS, otherwise we'll still be in graphics mode. And I don't really know what the original video mode was, so I'm being very lazy here. I'm just going to assume it was text mode, the mode 3, and so I just call the bias interrupt with mode 3 and the function number 0 restore video mode, or set video mode. And finally we quit our program. This is just the DOS terminate program function and the DOS interrupt. And here is where we tell the assembler what the name of the label is for the start of our program. So of course it was start, and that's it, we're done. So all that's required now is to exit, assemble and link this, and then we can run it and see what it looks like. Of course, to assemble our line drawing program, it's just tasm line, and it'll tell us there are no errors or warnings, which is great. And then we just do T-link to link it all together, and that runs quickly. So finally we can run our program and see what it looks like. So you'll notice it's on the screen almost instantly. It waits for a key press, press the key, and it exits to DOS. So it's extremely fast. It's so fast you can't really see how long it's taking to draw. You'd have to draw lots of lines to be able to see that. This is not the fastest possible way to draw lines, and I'll talk about some faster ways in later videos, but they require more advanced techniques. This is a fairly straightforward implementation. quite long, of course, for something so simple as the algorithm on the left there. But each step is fairly straightforward and easy to understand and follow. So it's a good starting point, but there are many things that we can do to improve this quite substantially. Having said that, the performance here is actually very good. This is not a slow line drawing program by any stretch of the imagination. Also, the executable is not so large either. If you have a look at that, it's only 682 bytes, and of course a good deal of that would just be the exe header. So very, very small program indeed. So anyway, that's a simple line drawing program, and in later videos we'll improve on this.